There are two types of propagation or conduction: saltatory propagation or conduction and continuous propagation or conduction. Propagation refers to how an action potential moves down an axon once it has passed over the axon hillock. So propagation refers to how an action potential moves between the axon hillock and the axon terminals. This is an example, an action potential, it's an example of positive feedback. As the ions flow into and out of the axon, the steps of an action potential, it keeps going, it keeps going, it keeps going. It propagates the stimulus rather than negating it. We have been generally talking about saltatory propagation previously in this class. That's the example that I've been using. Saltatory is a word that comes from the Latin root saltere, which means to jump. The myelin sheaths that cover axons, like these little pillows, these little purple pillows here, these myelin sheaths smother the ion channels on the axon, leaving exposed just little tiny pieces of the axon and just very few ion channels in what we call here a node of Ranvier. So in the node of Ranvier, the axon channels are exposed. So an action potential, once it passes the axon hillock, it is still capable of causing ion channels in the nodes of Ranvier to open and close and conduct electricity. And what this does is this allows an action potential to jump over each one of these myelin sheaths. By doing so, the action potential is capable of very fast conduction because it's only opening so many ion channels in the axolemma. This fast conduction, or saltatory propagation, is the preferred name for an action potential that has to move over a long distance. For example, the neuron that leaves your brain, goes down your spinal cord, out your sciatic nerve, and into your big toe, that is definitely myelinated because that is a very long distance for an action potential to travel. Conversely, continuous propagation occurs on unmyelinated axons, and it is an incredibly slow type of conduction. It's preferred for short distances, such as traveling from the left to the right side of your brain. I mean, honestly, most of the time it's used to travel from some point in the left side of your brain to another point in the left side of the brain. There are no myelin sheaths on the axon, and every single ion channel is exposed. And that's what you see here. These are all ion channels, and none of them are smothered with myelin. This means that an action potential will have to open and close every single ion channel in the axon in order to propagate the action potential. This takes a very long time since each individual ion channel has to be opened. This is called continuous propagation, and it's very slow. This situation reminds me of like when I used to go shopping with my mother at like ShopRite when I was like 8 years old, and I would try to just walk on the brown colored tiles on the floor like a certain color, and so you're like hopscotching over them, and my mom would be like, come on, hurry up. And then on the other end, you would just try to step on every single individual tile. And that's like continuous propagation. And still my mom would be like, come on, why are you doing that? So saltatory is fast, myelinated, long distance. Continuous is slow, unmyelinated, short distance. The speed of an action potential depends on two things. It depends on whether or not the axon is myelinated, but it also depends on how large the axon diameter is. That difference in axon diameter is substantial. I'm sorry, that difference of being myelinated or not is a substantial difference in terms of the speed of an action potential. These cross sections of axons are here, and we know that the axon on the left with the myelin would have a greater conduction rate than the axon on the right that's unmyelinated. Or is that true? The diameter of the axon also makes a difference in terms of speed and action potential. Larger axons are capable of conducting an action potential much faster than a smaller axon. In fact, that's how we classify nerve fibers. This phenomenon simply has to do with the number of ion channels that are available on the axolemma. Larger nerve fibers have a greater circumference, greater diameter, and more ion channels. Simply put, they're bigger, they have more. This contributes to a quicker graded potential that leads to threshold and a much quicker rise to positive 30 megavolts. So it makes it quicker to have an action potential. In reality, nerve fibers that are in your peripheral nervous system, such as the ulnar nerve or the sciatic nerve, they're classified by these two aspects of myelination and axon diameter. Large myelinated neurons, such as those in your sciatic nerve, they conduct action potentials very quickly. We classify them as type A neurons. Small, unmyelinated neurons, such as those that connect one part of your brain to another part of your brain in the same hemisphere, are very small diameter axons, and they're most likely unmyelinated. They're gray matter, since they're very short. Though they can conduct action potentials quite slowly, and we call these type C fibers. Type B is somewhere in between, right? Like it's a big category. It's somewhere in between those other two. And so we say it's intermediate size and it has a little myelination, but not a lot. Multiple sclerosis is a disease that attacks the myelin sheaths and is a great example of continuous and saltatory propagation. Some rogue B cell in some person's bone marrow, it decides to attack the myelin and degrade it throughout the body. And so what this does is this turns saltatory propagation action potentials into continuous propagation action potentials. So now an action potential going from the brain to the muscle in the big toe basically has to go through a lot more ion channels than it expected. And many times the action potential, it just simply does not get to its destination. And this is what accounts for the inability to activate muscles, especially some of the symptoms that are early onset of multiple sclerosis. MS usually attacks some of the cranial nerves first, leading to a loss of vision or a loss of hearing as some of those first symptoms. These cranial nerves, although small, are myelinated. And what you can see in this picture here, all of these little Y-shaped things are antibodies. And you can see that they're tearing away the myelin. And so an action potential that used to jump over the nodes of Ranvier now has to do this. And the stimulus is just not enough for that to happen. Over here on this side of this picture is something that I would introduce to my class in A&P2. This is a picture of how this rogue antibody is made by B cells and how it's a malfunction of the immune system. So basically, this MS is an autoimmune disease where your immune system starts attacking the myelin of your neurons.